Today we are going to do improper integrals. That what's so improper about them? Well, for one thing, let's say you want to integrate something where the upper limit is at infinity. Can you do that? Okay, like a function that you have that might have something that where the function is dying. Like the picture you see. See, the function is dying. Can we integrate all the way up to infinity? What that means is that you're going to integrate it up to a number called t, whereas and then you let t go to infinity to see if the limit exists. If it doesn't exist, then there's nothing to talk about. But if it does exist, then we'll call it we'll define that as the ability to integrate from a point to infinity. But remember that when we do that, we're referring to the limit as the upper limit becomes arbitrarily large. And similarly, we can also integrate backwards to negative infinity if you integrate from t to a number. Sorry, if you integrate from t to a number, and then but t is approaching negative infinity. Now, if both limits, that is from a point to negative infinity, I should say it the other way, from negative infinity to some point, and then from some point to positive infinity, both integrals exist by the limit definition, then we will say that the integral exists all the way from negative infinity to positive infinity. All right, so that is how the definition works. Now, however, if even so much as one of the integrals don't exist, then the integral does not exist. We're not going to care. Okay, if one of them goes nuts, is a goner. The whole thing is gone. So remember that. We don't care. And sometimes you might think, well, one of them go nuts, but maybe the other one balances him out. No, we don't care about that. Okay, by then the game's over. If one of them goes nuts, we kick them both out. So that's the plan for if you integrate from all the way from back to negative infinity and all the way up to positive infinity. So next, let's look at example 3.47, which says we'll integrate something, a standard, okay, a dying function. When you integrate to infinity, you most definitely want to do a dying function, because if the function goes up, then it's not gonna make any sense. Oh, by the way, if a function does make sense, if the limit exists when you integrate to infinity, it's called it converges. Okay, that is, the integral converges. Alternatively, if the limit doesn't exist, then it's called diverges. Now, the word diverges, don't let it give you the wrong idea. Diverge sometimes means you take off to infinity or something. It doesn't have to. Sometimes maybe it just go around, doesn't stop, it moves too much. Even that is called diverges, even though it literally, strictly speaking, didn't diverge. It's just, staying in the same spot, but doesn't stop. So converge means it come to one point. All right. So then let's look at example 3.47, which is the integral of 1 over x. And what happens if we try to integrate it from some point, say 1, all the way to positive infinity? Okay, now this function does die off quite a bit, right? 1 over x, it goes down, and as x goes to infinity, 1 over x goes to 0. So would the limit exist? Now, to do that, we are going to integrate it. Okay, take a page to the next page. We're going to integrate it from 1 to t. And what is the integral of 1 over x? Well, it's just the natural log, of course. And we calculate it from 1 to t. Okay, we're going by the definition now. And then we let t goes to infinity to see what happens. Now, notice this. We integrate first, then we take the limit. All right, and that's how the infinite integral is defined. So always remember that you're integrating from 1 to t. T is some large number. T is not infinity. It only goes to infinity. Remember what that means, because infinity is not a number. So t is simply a large number that you can think of, say a billion maybe. So we're integrating it from 1 to a billion, and you can integrate to a billion. Okay, there's no law against that. And what happens if you were to integrate to a billion? Well, by the time you do the math, you realize that this thing is going to go to infinity. Yeah, or something. Right. So if it goes to infinity, then you got a problem. So then this particular integral, 1 over x at least, if you are to calculate the its integral from 1 to infinity, it doesn't work. Okay, the region, the area is infinite, and then the integral diverges. So that's example 3.47. Please do that as your homework. Now, example 3.48, please do that as your homework as well. It's related to 3.47 with a bit of an interesting trivia. Otherwise, I wouldn't be having you spin volumes right now. And so please do that. And then we'll move on to, we'll skip 3.49 because that's pointless. And let's move on to 3.50. Now, example 3.50, we have a situation where we want to integrate from negative infinity all the way up to 0 of some positive function. Okay, notice that function is always going to be bigger than 0. It just happened to work out that way. Well, but it does have x squared on the bottom, so it dies fast on both directions, negative or positive. Well, is this thing going to converge? To know that, we're going to integrate it. So x squared plus 4 is a standard integration, which is the tangent inverse. Okay, it's in one of the rules in the back or something. Anyway, well, that's how you're going to pull it up. Okay, one of the rules in appendix A, page 700. Now, once you integrate it, and you remember that you're integrating from the bottom limit, you set it as t, and you imagine t to be an extremely negative number, such as negative a billion. Okay, so what if you were to integrate tangent from, say, negative a billion to 0? Then you do the math and realize that if you were to do that, the value will end up being very close to pi over 2. The inverse tangent function, if you don't remember what it looks like, just, well, go plot it somewhere, and you remember very quickly that that the inverse tangent is of let's see, as t goes to minus infinity, is simply pi over 2. Okay, and then the thing will come out very nicely. So please do this example as well, example 3.50. Next, let's look at example 3.51. Now this time we are going to I should write this down. We're going to integrate from negative infinity all the way to positive infinity of some function, xex. Now, to do that, remember the definition of this. To do that, you have to stop somewhere in the middle, maybe 0 somewhere else, doesn't matter. But we usually stop at 0 because 0 is usually easier to manage. So we're going to break this integral into 2 chunks, from negative infinity to 0, and then to 0 to positive infinity, which is fine. So we, and remember, if so much as one of them go crazy and go to infinity, both things get kicked out. They just diverges, they don't converge, the game's over. So but first, let's look at from negative infinity all the way up to 0. What happens there? We are going to integrate from negative infinity to 0. So we'll set t as the bottom limit. Okay, remember t is some kind of a large number, negative a billion maybe. That you keep in mind. T is a negative large number, but t is not negative infinity, okay? Because negative infinity is not a number. So t is a negative large number that approaches infinity. So say negative 1 billion. So you integrate that thing. How do you integrate that? First question, x e to the power x. You can use the integration by parts, where you let u equal to x, dv equal to ex dt, following the Liat rule, L-I-A-T rule, right? And or you can just flip to the back of the book and look at one of Appendix A, page 700, one of those rules. And I'm pretty sure xex is even, actually, I'm not sure. That's too easy. Maybe it's not in the back. Whatever. The point is, or maybe, yeah, it might be in the back. It might not be. But anyway, you will come out with the answer very quickly either way, okay? Because EX is usually easy to do. So once you come up with the integral, then you are confronted with this, calculating this particular limit, okay, which happens to be minus 1 minus t. What is that? E to the power t plus e to the power flower t. Now that one, the limit is good to do, except the middle term. Okay, t to the power t times e to the power t. Now that limit is not obvious because as t goes to negative infinity, say t is a negative a billion, then the t becomes big, but the e to the t, being its negative power, becomes extremely small. So what you have here is called the 0 times infinity situation in the L'Hopital's rule. If you don't remember the L'Hopital's rule very much, please go back and review it. In Calculus 1 is a quick review. Okay, you remember right away. You take the L'Hopital's rule means in a situation such as 0 times infinity, what you're going to do, and your book mentions that on the side, note to help you remember this thing. Okay, to do to do the L'Hopital's rule, all right, what you do is that it's in a situation of 0 times infinity. Now, L'Hopital's rule works on two situations, 0 over 0 or infinity over infinity. So what happens when you have 0 times infinity? Now, then what you happen, you force it into a 0 over 0 situation by pushing that e to the power t down to below the division line. It becomes e to the power minus t. And at that point, you can take the derivative of the top and the bottom and then come up with something. Okay, and that's the L'Hopital's rule. Yeah, please refresh your memory on that if that feels rusty, because we're going to be using the L'Hopital's rule quite a bit in this particular section. So after you crank all that out, you will come out that the first part of the integral from minus infinity to 0 is just -1. A very nice, clean answer. I love nice, clean answers. Okay. Now, next we will do the other part of the integral, which is the same thing, except we're integrating from 0 to positive infinity. Now, that one, we don't have to integrate. You know what? Because if you stare at it, what happens when x goes to infinity? Well, x becomes huge, right? E to the power x gets even huger. Okay, it just shoot up and you can't see it, basically. It goes up that fast, which means the integral is going to infinity, obviously, right? And therefore, this thing diverges. And remember, if one part of the whole thing diverges from minus infinity to infinity, the whole thing gets kicked out. Okay, the whole solution diverges. But you might say, but didn't we just figure out the first half is -1, and we went through a lot of work to get that? Well, too bad. You have to remember, if one part goes nuts, the whole part gets kicked out. So then so the answer is that it diverges and the integral doesn't exist. And so please do this example, okay, to feel comfortable with it, because we're going to be doing several things like this, especially the part that involves the L'Hopital's rule. And that's example 3.51. Next, let's look at a function that isn't continuous. Now, so far of all our integrations, or nearly everything except that infinity bit that we just did, well, all our integrations have the condition that you have to integrate over a closed interval. And why is that? The reason we define it that way is because if we don't require the interval to be closed, then sometimes your function might go nuts on the endpoints, like this. See, like this function. Like from the interval a to b, everything's good except that you look at the b end. At the b end, the function goes nuts. Okay, it goes to positive infinity. So how can you integrate it or not? Well, so far we haven't dealt with this situation, but we are going to deal with it now. Now this is a discontinuity, but only at the end point. So how are we going to do it? Well, we're going to do it like you might imagine. We're going to define such a function. So look at the definition towards the lower part of the page, where it says if f is continuous from the interval from point A to the open point B. That is, we don't include B. Okay, as long as B is not in the interval, we're okay, because f is continuous all the way through before B. Okay, any point before B, doesn't matter how close, as long as it's continuous there, right? So if that's the case, then we will define the integral from a to b as some kind of limit, okay, as the integral of a to t, where t is approaching b from the negative side, getting very, very close, but not actually touching it. It's just a limit, right? That's the meaning of limit, is we get very, very close, we don't actually touch it. So is like a technicality, in law. So, and if that's the case, then we can integrate it. And then and figure out if the limit exists. If the limit exists, then we'll say that the integral converges and equals to some nice value. If it diverges, then we'll throw it out and forget it. Okay, is a goner. And then and similarly, if the function is continuous all the way from a to b except some point in the middle where it took off, then maybe to infinity or negative infinity or both. One side goes up, the other side goes down. If that's the case, then we're going to define it at the integral as going, say, from, let's say your integral is going from a to b, right? Except that there's a point in the middle somewhere, see that your integral is having a problem. Then we'll just integrate it from a to c, and then from c to b with a formal definition. Yeah, that's that. Why is this thing blinking? I don't know. Maybe it's too bright. Well, whatever. The point is, then we integrate it in the middle and then see if things work out nicely. Yeah. All right. So, and remember, this definition, just like the previous definition, if we integrate something part way and then keep going, but one part of it goes nuts, then the whole thing gets kicked out. Okay, we don't care if the other part makes sense or not. Is a goner. We'll throw it away. So that is okay. So that's the new definition, and we will look at some example of it. Let's look at example 3.52. That's the integral of some function and 1 over 4 minus x. And as you can see, as x approaches 4, the denominator goes to 0, which is means this thing is going to go to infinity, right? Positive, being that being the square root sign doesn't accept, it's not going to pop up negative values. So then, so we are going to integrate this thing according to the definition, which means we're going to integrate it up to something called t, right? Because it doesn't actually go to integrate it from 0 to t, and then we let t approach 4 from the negative side and see what happens. Well, in this case, as it turns out, when t approaches 4 from the negative side, everything works out beautifully. The thing just equals 4, so we're good. So please do example 3.52 as your homework. Next, let's look at example 3.53, where you're doing x natural log of x, which is fairly straightforward until you notice that as x approaches 0, the natural log of x goes to negative infinity. In fact, it goes there fast. Okay, so then we need to integrate it and then let t goes to negative infinity. T goes to 0, okay, because t is the lower limit, let t approach 0 carefully and see if anything comes out of it. And if you do that, the integration then quickly comes out to be something that you're going to be stuck with doing the L'Hopital's rule again. So you do that, and to do the L'Hopital's rule is a 0 over 0 situation. So what you're going to do is push the t squared to the bottom of the denominator, becomes t to the power minus 2, and then everything should come out nicely, or something like that. Anyway, so then you end up finding that as t becomes gets close to 0, then everything works out okay. And then you actually come up with a number, and this improper integral does converge. So please do example 3.53 as your homework. Next, let's look at example 3.54. We're integrating from minus 1 to 1 over x cubed. Now, that's a very easy integration to do until you realize that you can't do it in the past because there's a 0 in the middle, and 1 over 0 dividing by 0 is not acceptable. But now we can do it, okay? Well, at least we can try following the rules, which says that we're going to integrate, being that 0 is a critical point, then we are going to integrate from minus 1 to 0, and then from 0 to positive 1. And if we figure out what those things are, then we can add it up, and then we'll be good. So then first, let's do from minus 1 to 0. okay, which oh, is that what we're doing? Yep. Which actually means we're gonna do from -1 to t and let t go to 0, because t is just a number that's very close to 0, and we can't actually integrate up to 0 because it wouldn't make any sense, because you might be dividing by 0, right? So we'll pick a t that's a microscopic number, such as you think of a 1 billionth something. Anyway, t is a very small number that is a very small negative number, because we're going from -1 to a negative 0.00001 or something like that, and then see what happens. Now, and then you notice that if you do that and you do the quick integration, this thing comes out to be positive infinity. Why? Because the t is still at the bottom, okay? And there's still a t at the bottom, so as it approaches 0, the whole thing just blow up in your face. Yeah. Wait a second. Let me see. Well, there's a small error here where it says that the answer of this is positive infinity. It can't be, because t is going to negative infinity, but t is being squared. And there's a negative sign there still. So that should be negative infinity. Not a big deal. Either way, it's blowing up, right? So then it's no good. And then therefore the entire answer also diverges, and there's no answer to it. Now you might argue something like this, because the here's a x cubed function, right? And then we only care about, actually, let's not care about that. Never mind. Yeah, it's 1 over x cubed. What does 1 over x cubed look like? It goes to infinity, right at a 0 on both sides, but the area might come out to be the same. That is, one part is positive and one part is negative. And a person might argue that it's probably something like this, right? And yeah, something like this, similar. And a person might argue that we're doing integration from -1 to 1, so then the positive and the negative cancels each other out, right? All the way to 0. It should all cancel out. So couldn't we call this 0? No, we're not. Okay, remember, if one of them doesn't work, the whole thing get kicked out. We don't care if it cancels out or not. All right, so I just want to quickly mention that. Not that it matters. In case somebody wants to argue for the integration, which I did sometimes when I was a kid, and I mean when I was your age. So let's look at the comparison theorem. Oh, before I say that, please do this example 3.54 as your homework. Next, let's look at the comparison theorem. The comparison theorem is used for, let's say you have two functions, f of x and then g of x, let's say, and where f of x is very hard to integrate. Okay, it has a bunch of weird parts and you can't find a rule to fit it. However, g of x, on the other hand, is very easy to do. All right, and then it just happens that way, that you found some g of x that's similar to f of x, but much easier. And also g of x, it just happens to be bigger than f of x for the entire domain of what we're talking about. And let's say f of x is bigger than 0 for the argument. So this thing is positive, this thing is slightly bigger than this thing, okay? And you can integrate this thing. Furthermore, the integral of this thing does converge. So this area converges, which that proves that this integral will also converge. That is, if this integral, okay, is equal to some number, say, or less than some you can prove that it converges equal to some number, then you know that the integral of f does exist. It does converge, okay? So this thing will converge if that is true. And as you can imagine, that also makes sense, right? So this thing isn't going to go to infinity or anything. But what if it oscillates? Well, it can't oscillate either if this is, I think this is for a closed situation or something. Well, whatever. The point is, yeah, maybe the closed situation isn't even necessary. All right, let's look at the condition. Okay, look at the next page, the comparison theorem, and theorem 3.7, which states that if f and g are continuous from a to infinity, all right, And then, so we're considering the entire positive area. So then in such a way that f is bigger than 0 and less than g for the entire time. And then if f goes to infinity, that is if f not just diverges, but diverges in such a way that goes to infinity, then obviously g goes to infinity because g is bigger than f. Similarly, condition 2, if g is if you can calculate the limit, I mean the integral of g, and it equals to some number L, then the f is also equal to some number m. Okay, so that is f will also converge and it will equal to some kind of a number m, and that number m will be less than L. So that is a fairly obvious, right? I mean, intuitively obvious thing to say. And so having said that, then we are going to do some examples. Next, let's look at example 3.55, where we integrate from 1 to infinity of 1 over x ex, e to the power x. Now, that doesn't look so easy to integrate. So, but however, it's happened to be easy to find some function that's somewhat bigger than it. Okay, and the function we're going to find is just get rid of the x and just say e to the power x. Now, the 1 over e to the power x is bigger because it's on in the denominator. Okay, and so then once it's bigger, then well, because the other denominator is bigger, so when you have 1 over, it becomes smaller. So then 1 over e to the power x, which is e to the power negative x, you integrate that, and that comes out to be from 1 to infinity, letting t go to infinity. As always, remember to use the t to remind yourself that we're not doing infinity, we're just getting close to it. Okay, and then that end up being just e, right? Now, if the function that's bigger has a limit, then the integral converges, that is, then obviously the original function also converges. So that's the end of that problem. And please do example 3.55 as your homework. Next, example 3.56, where we're supposed to prove that this thing diverges where p is less than 1. So yeah, pay attention to that. P is going to be less than 1. So p is maybe 1/2, which is the square root or cubic root or some other such thing. And then so for p less than 1, if we're going to prove divergence, we need to find something that's smaller than it that diverges. Okay, and the thing that's smaller that we're going to find is just x. Okay, 1 over x. 1 over x is smaller than anything that that has a power to it. Right. Well, I want to quickly mention this. That is, if you have a number x that is bigger than 1, okay, then x is going to be bigger than some kind of a power, as if the power is less than 1. All right, because well, that's because if the power is less than 1, you're taking some kind of a root, square root, cubic root, or some 2/3, some kind of power. And I believe we did this previously, maybe in pre-calculus, that you can show that this is bigger. Oh, your book is not showing that right here, so I guess I won't show it either, so that we can move on. But maybe you can look this up to see why this is the case. But because, let's see, is it bigger? Did I get it wrong? Yeah, it's bigger. Therefore, 1 over x is smaller. Okay, it's less than 1 over x to the power p. Being that x is bigger, then when you slap it on the fraction, then it becomes smaller. And so from this point on, then we have, of course, the integral of 1 over x. Let me stand over here. The integral of 1 over x goes to from 0 to infinity, diverges. We did that in the previous example. Example 3.47, and as a result, then the problem the book wants, when it also diverges, because something smaller than it is going to infinity, so it has to go to infinity too. So that's Okay, that's example 3.56. And let's see, so please do that as your homework. Now, with that, we have come to the end of the section, and in fact, I think the end of the chapter too. So that is pretty exciting. And so then well, at the end of the section, we have to do homework. So please do problems 349, 51, 53, 55, 57, 59, 61, 63, 65, 73, 83, 89. And then when you're done, I will talk about the problems in our next video. I also might talk about why that is true if I look it up. But if I do, we'll talk about it in the next video.